Hello and welcome to Clinical Optics Made Easy. My name is Wiggins. I've been teaching optics for about, 20 years now, and I'm really excited to speak to you now. We're going to go through lots of topics in optics that are going to be clinically important to you, not just in a testing examination, but to your career. And these are the same lectures that I've been giving residents all this time, and I hope that you find them helpful. So let's jump right in. So often when I start teaching optics, someone asks, why do I have to learn this? I mean, I get that cornea is important, glaucoma is important, retina is important, neuro is important. Why do I have to spend time on optics? Well, I can tell you that someone of probably no importance whatsoever once said that optics is really only important until your patient goes blind. And what that means is those rays have to get through the optical media and get to that retina. And if they don't, none of it matters. So optics may be one of the more important things. It's just that it's so fundamental to what we're doing that you often don't even realize that what you're talking about with the patient is an optics issue. But it's definitely worth your while to learn this. So here's what we're going to cover. You can see all of these wonderful things. We're going to talk about the assumptions, lenses, what you ought to get for a tattoo, and then at the end we're going to put it all together. So everything that I'm going to talk about in this lecture and in subsequent lectures comes directly from Clinical Optics Made Easy. And that's because that's where this book came from. My residents asked me for handout after handout on what I was lecturing, and finally said, well, if I'm giving out all these handouts, I might as well just put it together as a book. And so here it is. But in addition to the lecture material, this book contains over 800 practice questions. And it has section exams, and it has a final exam at the end. And, some of those questions, I've even put the answers to them in there. I'm just kidding. They all have answers in there. But in a lot of those questions, I write out explanations as to why the answer is the answer. So if you're interested in that book, I have a QR code down here, which I believe is what that thingy is called down there in the corner. And if you want to go directly to davisstreetpublishing.com, go right ahead. But you don't have to. By any means, you do not have to use my lecture material. I would be happy if you read any optics book that you can understand. Any optics book, meaning that not everyone will like the way that I phrase things. And maybe another optics book works better for you, and that's fine. My only concern is that you learn this material because I know that this is going to make you a better doctor, and that's what I'm really interested in. So find you something that works. Work lots of problems. So to kick things off, we're going to talk about vergence. Vergence, as you can see, is the movement of light rays, and light rays can really only do one of three things. They can either diverge, get farther apart, they can converge, get closer together, or they can stay the same distance apart, which we will call parallel rays. There are some assumptions that we need to know in optics to help us along, and the first one is rays coming from an object diverge. You can see that in the diagram above. I have red rays coming from my object, that arrow, and those red rays are getting farther apart, so they are diverging. If I had a dioptric value on that, it would be minus. If you don't know what a diopter is, wait a few slides, you will. But rays diverge from an object. Number two, in optics, rays go left to right. That's our convention. And it will always be left to right when you're reading an optics problem, unless somebody comes along and says, dude, in this case, it's going right to left. But that almost never happens. It's almost always left to right. Number three, rays from the sun or from an infinite distance away are parallel, meaning they have zero vergence. What is an infinite distance? Well, in optics, infinity is 20 feet away or more. I know that sounds kind of stupid. I mean, it's only 20 feet. It's definitely not an infinite distance, but in optics it is. So if it's 21 feet is where your object is, those rays coming at you are considered parallel. And the very last thing that we're going to assume, at least for this lecture series and in nothing else in life, is that the narrator knows what he's talking about. So most times I would say take that with a grain of salt, but hopefully when we're talking optics, that's going to be true. It's great to know what vergence is, but how can we manipulate vergence to help our patients? To do that, we're going to need some sort of device. As you may have guessed, it's called a lens, and there are two main types, plus and minus. Hey, how old do you figure that technology is? Turns out, pretty doggone old. You can see here 750 BC with a power of plus 8.3 diopters. How about that? So yeah, we discovered this lens from 750 BC, but how do we know that it's really a lens? I mean, what makes a lens? Well, it takes three things. It's got to be curved. And I mean, that should be pretty transparent to you, pun intended. If you think about the window in your bedroom, it's flat, it has no curvature. The rays going through there, they're not converging, they're not diverging, they're staying parallel. So it is not a lens because it is a flat, transparent surface. The third thing that makes a lens is that the lens has to be made out of something different than what it's in. It has to be in a media with a different refractive index of what the lens is. So think about if you hold up a glass lens, it's in air, right? So it's not made out of air, it's made out of glass. So it's in something different than what it is. Another example, let's say that I had a piece of ice and I was able to give that ice some curvature and the ice just turns out to be very clear and transparent. That piece of ice would be a lens. It would converge or diverge depending upon which way I shaped it, but it would be a lens until I drop that piece of ice into a bucket of water. Now, the lens, the ice, is surrounded by water, and it's all the same material, so it would no longer cause vergence one way or the other. So we're going to start with the plus lens. As you can see, the rays on the left are parallel. There is zero vergence, and in optics, again, rays always go left to right. As the rays hit the lens, it converges to a point. And in this case, it's converging to a focal point. Focal point, guys. Come here. Focal point. There you go. So now we're going to take a minus lens. And so here we have some parallel rays, and they're going to hit these minus lenses, or this one in particular, and the rays are going to diverge. They're going to get farther apart. There is no place out on the right-hand side where those rays will ever get together, which is a little bit sad. But if we draw a ray backwards along those diverging rays, we can see that back behind the lens on the left-hand side, there's a spot where they get together, and that's called a virtual focal point. So it turns out that every lens does have a focal point. So now we have plus lenses, we have minus lenses, we know what vergence is, but not every lens is the same. There are different powers of lenses, thank goodness. And so we need to have some sort of system to talk to one another and describe the power of a lens. And so for that, as in anything, you need standardized units. And for optics, we have what's called the diopter. And the diopter will tell us how much convergence or divergence that lens is expected to give. So where does the word diopter originate? You don't care. But what you do care is that one diopter is 100 centimeters of vergence. So you can see here on my diagram, I've got parallel rays. I'm hitting one diopter of power for my lens, and it is coming to a focal point 100 centimeters away. So that is the definition of a diopter and how all lenses are measured. Now, although the focal point is 100 centimeters away, the actual distance from the lens to that focal point is termed focal length. And that, my friends, leads us to our first formula. Diopter equals 1 over the focal length in meters. And if in your brain you're asking, do I really need to remember that? I promise that anything that I talk about, you really need to remember, because I only talk about things that are hopefully going to make you a better ophthalmologist. So we can see here that diopters and focal lengths are inversely proportional, and if we did the math on that, we would say 1 diopter is 1 over 1 meter equals 1, and that's a whole lot of ones. But this formula will allow us to do this. What is the focal length of a 2 diopter lens? And so it gives you some choices here, and we're going to apply our formula, and hopefully you're not going to pick number 1 because number 1 is in diopters and it's asking you for focal length. So let's work the problem. So here we go. We've got our formula set up. 2 diopters equals 1 over x in meters, and suddenly you realize that now you have to use 8th grade algebra. Or you guys are way younger than I am, so nowadays it's probably 3rd or 4th grade algebra. So we have to do that old cross-multiplying thing where we have 2x equals 1, and then we have to isolate the x, and so we've got to divide the 2 to both sides, and so x equals 1/2 meters. It's just a lot of thinking, and it seems really hard. I wish we had a shortcut. Hey, have I ever let you down? Yeah, it's early. So it turns out that if you divide the power of the diopters into 100, you get your answer in centimeters. I mean, it's in centimeters, but you get your answer, right? And so 100 divided by 2 equals 50 centimeters. If you had to have that in meters, I mean, you're smarter than I am. You can take that metric system and manipulate it any way you want to. But it's a great shortcut. It's going to come in so handy for you. So in optics, centimeters are going to be your best friend. And right here, we have our first tattoo recommendation. I know what you're thinking. You really want to work some more of these problems and see that this shortcut works. So let's go. What is the focal length of a 5 diopter lens? And so we're going to use our shortcut. What is 100 divided by 5? That's correct. 100 divided by 5 is 20 centimeters. Want to see something even cooler than that? We just did diopters to focal length, but what if we had a focal length and we wanted to know the diopters? What is the power of a lens that has a focal length of 25 centimeters? So we can take those 25 centimeters and divide those into 100, and we get our dioptric value. It's wonderful. The formula works both ways. That's less for us to think about. You probably saw that coming because the formula is inversely proportional, but it doesn't matter. We take something, we divide it into 100, and odds are really on our side that we're going to get the right answer here. So it doesn't matter. Focal length to diopter, diopter to focal length, divide into 100. So do we have it? Do you want to work some more problems to make sure that you have it? Hey, let's do that. Okay, I want you to grab a piece of paper. No, not that one. Grab that one right over there. Yep, that's the one. So grab that piece of paper, and I have some dioptric values for you. I want you to put me on pause and figure out the focal lengths for all these lenses. I know it's hard to put me on pause. I'm such a delightful speaker, but you can do it. Put me on pause, work these 10 problems, and then let's see how you do. And we're back. Hopefully these are the answers that you arrived at. We were just dividing things into 100. 100 divided by 4 is 25. Notice that with plus 3 minus 3 diopters, the answer is still 33 centimeters. Now, the focal points are obviously in different locations. For a plus 3, it's going to be 33 centimeters off to the right of the lens, and a minus 3, 33 centimeters off to the left. But the length is the same. Hey, look at number 10. We had to have a calculator for that, right? Because who knows what 100 divided by 16.7 is? Well, it turns out it's 6. As you work lots of these problems, and you should, you will start to learn that 100 divided by 16.7 is 6. There are a few of these numbers that we'll do over and over that'll just kind of lodge into your brain, and you won't need a calculator past that. Let's shift gears just a little bit. So we had dioptric powers, and we turned them into focal lengths, and now we have focal lengths that we're going to turn into dioptric powers. You can do this. I believe in you. Grab that piece of paper, take these things, shove them into 100, see what you get. All right, you ready to go? Go ahead and put me on pause. Wait, before you put me on pause. Just kidding. Go ahead, put me on pause. Hey, thank you for unpausing me. Here are the answers. Let's first look at number 5. And number 5 looks kind of weird, and that's because these questions can be pretty boring to write for optics writers. And, you know, as a group, optics people are just wild and crazy party animal kind of people, and we like to spice things up. And the way that we do that is that we give you an answer that's less than a diopter because that's somehow fun for us. I don't know how, but anyway, it is. And that's why that one looks the way that it does, because we don't want to keep using the same old numbers over and over. But let's, more importantly, look at number 7. See that 40 diopters equals 2.5 centimeters. That is very clinically relevant for you. Why? Because of the corollary. 40 centimeters equals 2.5 diopters. Why do you care? Because by and large, most of your patients like to read their books about 40 centimeters away. And so in their bifocals, you will be prescribing 2.5 diopters more often than not. Now, that's not to every patient. Everyone's a little bit different, but through your career, you will see that when you're giving bifocal power, it just seems to be 2.5 all the time. And that's why, because of those 40 centimeters. So that relationship is important. Notice on number 8, we're back to that 6 diopters into 100 is 16.7, or 100 divided by 16.7 is 6. So once again, you're going to see that relationship over and over, and hopefully it'll just become second nature, and you won't have to have a calculator past that. So I have a special treat for you here. What I've got right here is a trial lens set from what we believe is around 1850s perhaps. And so we're going to open this up and see what we've got in here. And you can see it looks a whole lot like the lens drawer that you likely have in your clinic, although the lens style has probably changed quite a bit over the years. What you're seeing down here is a cataract instrument from the 1860s, and that's a topic for another day. But the interesting thing about this old set is that it's not labeled as plus or minus. It's labeled as concave for your minus lenses and convex for your plus lenses, as we were talking about the shape of the lens. So what we're going to do is we're going to take a plus 10, this old thing here, and we're going to take a minus 10, and we're going to shoot light rays through these, and we're going to see how they're calibrated and see about these focal points that we've been talking about. Okay, we're going to do our very first experiment. We've got a tape measure laid down here. It's in metrics. I have a sculpture dude that my son built for me many years ago, and I have him standing right at 10 centimeters. So the first thing I'm going to do is I'm going to take a plus 10 lens. I have a light source well away from me, and you can see that it comes to a fine focus right where the guy is standing. And as I go forward or backwards, I'm going to lose that fine focus. But this is well calibrated as a plus 10 lens. 100 divided by 10 is 10, so it should have been at 10 centimeters, and it was. Now I'm going to take a minus lens, and the minus lens has a virtual focal point, so it should show up nowhere on there, and you can see there is no fine focus for that. So that is our first experiment. Now that we've done our very first experiment, we're going to do our first clinical correlation. That is something that we do throughout the book and something that we'll do here in the lectures. You have the right to always ask, how does this help me become a better clinician, a better surgeon? And we as instructors should always, hopefully, have an answer for you. Everything should translate. We are not undergrads anymore. We are not medical students anymore. We are practicing physicians. We may still be in training, but we are learning our craft, and everything should be worthwhile. It should be worth our very precious time, because as you know, you have very little time for anything right now. There is so much to learn, so everything should have value. So that's me standing on my soapbox right there. Feel free to always ask your instructors, how does this clinically apply? So here we go with our first clinical correlation. We have an emmetropic pseudophake who wants computer glasses. What's an emmetrope and what's a pseudophake? We're going to get into emmetropia here in just a few slides, but basically just envision someone who can see off at a distance with no effort whatsoever, and they cannot see up close because you've done cataract surgery on them. You've taken out their lens. You've given them an artificial lens, which is what a pseudophake is. And if you've given them a monofocal lens and you targeted for distance, then odds are they may have some trouble seeing up close, and that's the case here. So they want to know, what power of glasses do I need to see the computer screen? So what you need to know is how far do they like to sit from the computer screen, and once you have that focal length, you can convert it into diopters using the formula that you've learned from this lecture. Now, how far away do you think that is? I'll tell you what, let's do an experiment. I want you to put me on pause. I want you to sit comfortably from your computer and measure how far away your eye is from that computer screen. So go ahead, put me on pause. Get your distance converted into centimeters, and then let's see what you got. Okay, we're back. I am going to think that you measured somewhere around 67 centimeters. Am I psychic? Maybe so. But in this case, I knew the answer because most people like to sit arm's length away from their computer screen. So for most people, that's going to be somewhere between 65, 67 centimeters. And once you have that value, you will then divide into 100 to get the dioptric value that you should be prescribing for this patient. And in this case, 100 divided by 67 is 1.5 diopters. You'll see that value kind of over and over as you're prescribing computer glasses to folks. But that is the very common distance. You would take that 1.5 and you would put it on top of their prescription. If they're a true emmetrope and they don't need a distance prescription, then it would just be plus 1.5 to give them the best chance of seeing that computer screen the way that they want to. Now suppose your kid comes to you and she wants to burn ants on the sidewalk, and she's got a 20 diopter magnifying glass and she just can't seem to get it to work, and she's coming to you for help. You know from this lecture that if we take 100 and divide it by 20, we're going to get the focal length that she needs to wipe out that ant who wasn't really bothering anybody. And of course, 100 divided by 20 is 5, and so she goes out there and holds it 5 centimeters away and just lays waste to that innocent ant, making you a better parent through optics. So let's take what we've learned a step further. Here in my diagram, you can see I have an object on the left and the rays are diverging, and rays go left to right. It's hitting this lens and the rays are converging, telling you that it's a plus lens, and that forms that upside down arrow. Wouldn't it be handy and hopefully clinically relevant if I had a way to know exactly where that image is going to be? Maybe a formula. Yeah, a formula would be great. You asked for it, and here it is, the simple lens formula. This formula is huge. It is our bread and butter formula in optics. It is extremely clinically relevant. It may not be apparent to you yet, but stick with me and I will show that to you. But let's walk through this formula that we're going to use over and over and over and over and over. U is the vergence as it strikes the lens. D is the power of the lens, and V is the vergence as it exits the lens. If that doesn't make sense, bear with me. So I want to spend some time getting into U plus D equal V before we get more into the clinical relevance, because it's so important that we understand this. So in this example, I have light rays that are hitting a +4 lens and want to know where it comes into focus. So it tells me that the object is 20 feet away or further because it's telling us that it's coming from infinity. That tells me that the vergence of those entering rays is 0, parallel rays. So that's my U. My U is going to be 0. It's also telling me that it's a +4 diopter lens, so I have my D. So I have 2 of the 3 variables. I just have to solve for V. So obviously, V is going to be +4 diopters, but it's not wanting to know what is the dioptric power of V. It's wanting to know where the image is. And for that, I do what we've already learned. I convert into centimeters. So 100 divided by 4 is 25 centimeters. And I will tell you that because V is positive, I know that it's going to be to the right of the lens. Had V been -4, the image would have been 25 centimeters to the left of the lens. But what if U were not 0? What if the rays coming into your lens were not parallel? That's what this example is showing us here. It's got an object 10 centimeters left of a lens. It's asking us where's that image going to be? Or actually, no, look at that. It's not asking where the image is going to be. It's telling you where the image is going to be, and it's asking you the power of the lens. But it's a simple lens formula, and it's giving you 2 of the 3 variables. So we're going to write down what we know and solve for the 3rd. So I want you to pause me right here and see if you can figure this out. What is U? What is V? And once I know that, I can calculate for D. Okay, welcome back. So U was 10 centimeters to the left of the lens. And remember, when the rays diverge, that's a negative dioptric value. So it's not +10, it's -10. Obviously, we don't know D. V, it said 20 centimeters to the right. So that makes it positive because it's on the right. And 100 divided by 20 is 5. So now I know U, I know V, and I can figure out D. So here you go. And D is 15 by the powers of basic mathematics. Okay, here's another one. I've got an object 25 centimeters left of a +10 lens, and where is my image going to be? How are we going to work this problem? The same way. We're going to write down what we know and figure out what we don't. So let's see here. We got 4 choices. We're not going to pick choice A because it's asking us for a location. So put me on pause and see what you can figure out. Okay, well, hopefully you got the choice B here. U was -4. Hopefully that didn't trip you up. 25 centimeters left of a +10 lens. 100 divided by 25 is 4. Minus because the rays are diverging. If you said +4, you're going to end up doing the wrong math. But -4 here, we know what D is, and then +10 and -4 is going to give you a +6 is the dioptric power, but we wanted to know a location. So 100 divided by 6 diopters gave us 16.7 centimeters to the right of the lens, and we know it's to the right because it's a positive value. Starting to get a little hungry here. We've been going for a little while. Anybody got any chocolate Pop-Tarts? That just sounds really good right now. Or Oreos. Oreos would be really good too. You ever have those mint Oreos? Man, those are the best. Well, sans Oreos or Pop-Tarts, I guess we'll just move on with optics. Here we have an object 33 centimeters away that hits a +5 lens, and where will that image be located? So here you have your 4 choices. Once again, put me on pause and see what you come up with. Hopefully here's what your math shows, because it's what my math showed. An object 33 centimeters away, so U is a -3 because rays are diverging in optics. We go left to right. It's hitting this +5 lens, and by the power of simple mathematics of single digits, we have 2 diopters, and then 100 divided by 2 is 50 centimeters, and it's +2, so it's going to be 50 centimeters to the right of a lens. And keeping with the same theme, let's work another U plus D equal V problem. Here we have a 14 diopter lens. Hey, did you know that before we had the 20 diopter indirect handheld lens, we used 14 diopters? Now this was back in the day, and you probably never see one in your whole career, but there were 14 diopter indirect ophthalmoscopy lenses. It gave a bigger image and a smaller field of view, but I don't know, just a little historical trivia there. Back to relevancy. Here we have a 14 diopter lens that forms an image 25 centimeters to the right of the lens, and where's that object? Okay, put me on pause and work the problem. Hopefully you picked D, 10 centimeters left of the lens. It gave us the power of the lens at +14. It gave us the location of the image, which we had to convert to diopters, so 100 divided by 25 is 4. And with 2 of the 3 variables, we could mathematically figure out that U had to be -10. And since it's minus, it's 10 centimeters left of the lens. And remember, that was -10 diopters, and we divided that into 100 to get to our centimeters. Want to see U plus D equal V in action? Well, here we go. I have my object, which is my light source in this case, setting 120 centimeters from that wall, but I'm going to hold a +6 diopter lens 20 centimeters from the wall. So the distance from the object to the lens is going to be 100 centimeters. So what's U? U is going to be -1. Again, D is +6. What does that make V? +5. So that's going to be 100 divided by 5, 20 centimeters. And the guy that I've got right there is standing 20 centimeters from that wall. So watch the lens, and it should come to a nice fine focus when I get to the dude. And then if I go further, I lose it. If I go back to him, perfect. And I come back, and I'm farther than 5. So U plus D equal V does work. Our second tattoo recommendation, and this one even more than centimeters. Is it more than centimeters? I don't know if it's more than centimeters, but it's extremely, extremely important. This is a great tattoo to have. I appreciate my retina buddy here getting that tattoo for me, even if it's only in Sharpie. He took one for the team there. Great formula. So here's what we talked about so far. It seems like we've just gotten started, but already we've covered a whole lot of things. I promised you that we would continue to get more clinically relevant, and that's where we're headed next. So let's get into some refractive errors. And we're going to start with a unicorn. Her name is Emmetropia, and Emma is a genetically superior being. She has the perfect amount of convergence in her cornea and the perfect amount of convergence in her lens that make those parallel rays coming in converge perfectly onto her fovea. She is amazing. She can see 20/20 or better off at a distance, and she's not bothering to come in to see you. Here's who you are going to see. This is myopia. Myopia is a convergence overachiever. These are the people that sit in the front of the room, take all the notes. They're the gunners. They're wrecking the curve. They are the overachievers of the eye world. And so most ophthalmologists are very likely myopes. You look at this guy, and that cornea is converging too much, or that lens is converging too much. And as you can see, all that convergence from rays coming in parallel are leaving you focusing somewhere in the vitreous, somewhere in front of that fovea. And that's why when myopes look off at a distance, everything's blurry. It's because those rays are not on the fovea. Now, why are they myopic? Why do they have all that converging power? Could be from different disease processes. You can see what's listed here, but one I want to point out is called axial myopia, and that means that the eye is longer than the average eye. So it could be that it's a normal amount of cornea curvature, a normal amount of lens curvature, but the eye is too long, and so the target, the fovea, is further back than what you saw in Emma. Now, here's the polar opposite of myopia. These guys are the underachievers in the convergence world. They sit in the back room, they talk during the lecture, they don't take notes. They are the convergence underachievers. And so in these guys, the cornea doesn't converge enough, it's too flat, or the lens doesn't converge enough, it's too flat, or in axial hyperopia, the eye is shorter than the average eye. And so even though they may be converging enough up front, the target is moved forward, and so they really aren't converging enough. No matter what the problem is, these guys don't converge enough, and that focal point gets back behind the eye. Now you say, how can the rays get behind the eye? The back of the eye is not transparent. Well, that's true, but in ophthalmology, we like to pretend a lot of things, and the first thing that we're going to pretend is that the eye is invisible in the back of the eye. Tell that to your retina colleagues. And when we don't converge enough, those rays will pass right on through and converge back behind the eye. You can see here a list of things that could cause that to happen. Now we're going to talk about a really useful concept called the far point. The far point is the farthest away an eye can see without any help. That means without glasses, without contact lens, without a monocle. Wouldn't it be cool to prescribe somebody a monocle? In 20 years, I've never had that opportunity. I really want to before I retire. So if you know someone that's needing a monocle, send them my way. But without any help, the farthest away an eye can see is called the far point. Now, when we're talking about Emma, Emma's far point is infinity. So with no help at all, she can see that far away. She's a genetically superior being. She's a unicorn. You'll probably never see her. For a myope, where is their far point? Because you see here, when they look off at a distance, the rays focus somewhere in the vitreous and everything is blurry. So look right here at this bottom diagram in a myope. You can see that the rays coming from an object are diverging. And when that divergence hits that over-converging system, it weakens it. And so instead of that focal point being in the middle of the vitreous, it's pushed back to the fovea. Does that look a lot like a U plus D equal V problem? How about that? So we have U and we have D, and then that determines the V. So when U was 0 in that top diagram, V landed somewhere in the vitreous. But when U becomes negative, there is a point out there where that eye it's looking at something that's close enough to where the divergence overcomes that overconverging system and pushes that focal point back onto the retina. And that's why every myopic eye has a place somewhere between the eye and infinity where they can see clearly without any help, and that is called their far point. So far point for a myope, somewhere between the eye and infinity. But look at the hyperope. Their rays are coming to a focal point back behind the eye. So if they were to look at something up close like a myope did, they would get extra divergence, and that would push that focal point even farther behind that eye. It just doesn't get any better for these guys. So when we talk about the far point for a hyperope, Some people describe that as beyond infinity because it's back behind the eye, and it's somehow that means beyond infinity. I've never understood that term, but some optics teachers use it, and that's, bless their heart, perfectly fine. Do as they instruct. But you and I are going to never use that term again, number one. Number two, we're going to call it behind the eye because that sort of makes sense to me. So their far point is an imaginary focal point back behind the eye, and because that's true, the hyperope is kind of screwed. There is no place that they can clearly see without some kind of help. So here are some rules that I have about far points, which is just kind of a recap of what we've been talking about, that the emmetrope has a far point off at infinity, and for myopes and hyperopes, you can read that here. But the important thing is that far points do not change. Your lenses can change, the position of the lens can change, but the far point of that eye does not change unless something major happens to that eye, such as an ophthalmologist comes along and does surgery on that eye. But otherwise, the far points do not change. So let's put some lenses on refractive errors and see what happens. Now, what would happen if we put a minus lens in front of this eye? This, once again, is a U plus D equal V problem. U is 0 right here because these rays are parallel. And it hits D, and then that calculates V. But now we're going to change the U. And we can do that by having this eye look at something up close. We know that when we look at things up close, that the object is now inside of 20 feet. It's no longer at infinity. It's going to give negative vergence or divergence. And that is going to overcome a strong convergent system and push it back to the fovea if we pick the right distance. Now let's just draw a line right here. Okay. This is the far point for this eye. We know that because if that eye were looking at an object at any other distance, that focal point would not be right on the retina. It'd either be in front of it or behind it, depending upon how close we hold the object. Because as you move the object one way or the other laterally, that focal point is going to move right along with it because U plus D equal V. But let's suppose that I take the eye, have them look off at infinity, and put a minus lens in front of the eye as they're doing it. So here I have a minus lens. You can see the focal point of that lens in the red rays here on the top diagram. And I'm going to draw that line again. And you can see that that focal point for that lens is right on the far point for that eye. We look at the bottom diagram, we can confirm again that that is where the far point is. And when we're doing manifest refraction, what we're actually doing is trying on shoes. We're trying on different lenses until we find the one that fits. More technically, we're trying lenses with different focal lengths until we find a lens that has a focal point right where the far point of that eye is. Does that make sense? Manifest refraction is looking for the lens that has a focal point where the far point of that eye is. They have to line up for that to be the lens. Here's a hyperope. You can tell because the rays are going right through the eye, and the far point is going to be back behind the eye. And right below it, you see we have a plus lens, and the lens is converging rays, as plus lenses are known to do. And if we draw a line from the far point of that eye, we see here that when we have the plus lens at this particular location, and it has a focal length as shown, it's falling right where the far point of that eye is. So that is the lens for that particular hyperopic eye. And again, when you're flipping the dials through manifest refraction, better one, better two, you're looking for that guy right there, that lens. You are looking for a focal length that's going to hit right where that far point is. And when you do that, that extra converging power of that plus lens is going to pull that focal point up to the retina because you're adding convergence to it. So when U plus D equal V, you're adding to the D by adding another plus lens. So when we talk about why do hyperopes need plus lenses, it's easy to see here. Hyperopes don't converge enough, and so we're adding converging power. Another way of thinking about it is that a plus lens has its focal point off to the right. A hyperopic eye has its far point off to the right. So that's why that kind of lens works on that kind of an eye. If you think about a myope, their far point is on the other side. It's on the left-hand side of an eye. So they need a lens with a focal point on the left-hand side of the lens. And a minus lens has that. That's why minus lenses are used to treat myopes. You could also say that a myope has too much converging power, and so we need a lens that diverges or reduces converging power. Now try to work that into a conversation at your next cocktail party. You'll either sound really smart or really weird. So here's what we covered, just a whole lot of things, and I'm going to leave you with some homework. I'd like for you to work lots and lots and lots of U plus D equal V problems, and then I'd like you to work a few more. This is so important. You've got to get this down cold. Also, take a little bit of time and work your converting focal lengths into diopters, diopters into focal lengths. These are the very basics of optics. These are the building blocks. These are the things that you're going to use your whole career. It's worth your while. If you're taking OCAPs or the boards, these are the kind of things that you're just expected to know, that everyone is getting correct. So you need to make sure that you are getting these correct too. Well, that's all we have for this very first lecture. I really hope that you come back and join us again for some more Clinical Optics Made Easy, because next time we're going to talk about the mysterious world of astigmatism. It is a very high yield topic for our field, and we're going to go into it in quite a bit of depth. So once again, thank you for your time. I'm Wiggins. This is Davis Street Studios. I hope you all have a great day. Thank you.